That was loud.
Go ahead.
Good morning, everyone. My name is Gus Merwin, and today I'm going to talk to you about something that I find extremely fascinating and I really think can change the world. It's an alternative form of energy that very few people know about and very few people are interested in because it does fall under the category of nuclear energy. The energy does come from fissioning of atomic nuclei. However, it's a different fuel. It's thorium rather than uranium. The main difference being the fertile isotope that you start with is thorium-232. It is then bred into uranium-233 and then fissions. The main difference here is the fact that uranium-233 is not good to make weapons. In its radioactive decay, it emits an extremely strong gamma ray, which destroys electronics. This means when you try to build a bomb out of it, all your timing sequences and circuits get destroyed. In the 1960s, we built a program specifically based around thorium, and it built a perfectly successful reactor that ran for 5 years. During this program, there was also a parallel program to study uranium-233 as a weapons material, and it was decided that it was not advantageous and it's easier to start with natural uranium and go through a classical enrichment process, which is extremely difficult. This proves how hard it is to make a bomb out of 233. In addition to just the proliferation aspects of thorium, the other larger implication is the safetiness of these reactors. Specifically, they're molten salt fueled thorium reactors, so the fuel is actually a liquid. It flows through the core, and it's because we're all technical people here, we understand the concept of thermal expansion. The basics of nuclear physics indicates that the amount of fissioning going on in the core is proportionate to the amount of fuel in the core. It makes significant sense. The catch is the fact when your core gets hotter, the liquid expands, meaning that there's less fuel in the core and the reactor power goes down. It is a naturally stabilizing reactor. It's a passive control system. You have no external operator that has to insert control rods. So things like the accidents at Chernobyl, Fukushima, and 3 Mile Island, all which were caused by lack of operator control or what was needed is additional cooling, at least in Fukushima, these all become irrelevant because your reactor cools itself. There's even an additional one, which is called a freeze cap, an additional safety measure. At the bottom of a reactor, you have a fan that's powered by the reactor that blows cooled air across a small open plug, keeping the salt frozen in a solid state, and the hot salt flows on top of it. If the reactor power gets too high, this gets too hot and the fuel melts, draining the reactor and shutting down your reaction. Pretty incredible concept, passively safe. As I mentioned before, this was all done. From 1961 to 1966, a reactor, molten salt fueled on thorium and uranium, was ran for 5 years at a power of 5 megawatts. I'm sorry if my numbers are slightly skewed. But it ran without major concerns. Corrosion, which was cited as the reason it was stopped, was not actually a major issue. If you look in the literature, it was essentially not really a problem. And the fuel is incredibly cheap. Thorium is much more commonly found than uranium-235, which is current nuclear fuel. It is about as abundant as lead, whereas normal uranium-235 is about as abundant as platinum in the Earth's crust. So the classic thorium phrase is, why are you spending all this time burning platinum and building enrichment plants which make bombs when you can just burn lead and it's cheaper, more abundant, and passively safe. It doesn't have the active response that uranium does. And I believe that's really short.
You're done? That was about 350.
No, not terribly short. Yes?
The energy output of thorium reactors versus uranium reactors, is it compatible? Is it the same?
Yes. All nuclear reactions have roughly 10 million times the energy density of chemical reactions, at least energy per bond. And there is a slight difference in binding energy of uranium-233 versus 235, but it's insignificant comparatively. The 100 grams of thorium, natural thorium that comes out of the Earth's crust, would provide all the energy that you would use throughout your life, including transportation. It's about the size of a baseball, fits inside of your hand. And I forgot. Never mind. I can't add to it.
What did you forget?
What did you forget?
There's no radioactive waste. What you burn in normal reactors is just the 235, but it only starts off with 1% of natural uranium. And so what you're left with is 99 essentially percent of your fuel, which is 238. This is the stuff that has to be stored in Yucca Mountain, and because it breeds a lot of plutonium, is radioactive for 10,000 years. Thorium, because you're only burning this single natural element, or isotope, you burn 100% of it. There's no radioactive, well, it's radioactive, but for a much shorter time, roughly 300 years rather than 10,000. And you burn all of it rather than just 1%. Yes?
Sounds like a perfect fuel. So what's the catch and why didn't we start using it 50 years ago?
The catch is when the United States, which developed all nuclear power and then was essentially followed by the rest of the world, we were also more concerned with making bombs to fight the Soviet Union. And the uranium development program followed both. It goes really well with submarines for technical reasons, and it also breeds fuel for bombs. And so we figured that we can have the commercial side develop this technology, and it'll expand, and we'll get really good at breeding plutonium. Problem is, everybody else in the world did the same thing, and now everybody else in the world is breeding plutonium, which makes bombs.
So there's no technical limitations
No,
right now?
it's completely done. It was done in the 1960s.
So why isn't it done now, though?
They're trying to be, but the first one is
What's holding it up from being done?
$1 billion.
Hasn't worked yet.
$1 billion.
Oh,
Yeah, I'm aware of that, yes.
What about the corrosive
The
properties?
future of energy does nothing.
There was a huge metallurgical process done at Oak Ridge National Labs prior to the 1960 program, and they developed Hastelloy N, which is a modified nickel chromium molybdenum metal, and the corrosion rate was found to be something like 1 mil a year, which is a millimeter, or a millionth of an 1,000th of 1 inch per year, which is entirely acceptable, well within design tolerances.